Thank you very much for the kind introduction and especially for being invited, for being here. This has been tremendous so far, and it promises to continue that way. You've assembled an extraordinary range of people here. I've learned so much about the developing brain, for example, and it's just great to be here. The first time I met Stan actually was in November 2018. There was a human single neuron meeting at Caltech, and afterwards there was a poster session outdoors because the weather was sunny. It was Southern California, and Stan came and he was wearing a hat, and I found out later how smart that was because I got badly sunburned. You might have noticed we have somewhat of a similar haircut, and so was the first thing that he could impress me with, and then we started collaborating on representations, part of which I will be talking about also today. So I'd like to first explain how we get to record the activity of single neurons in the awake behaving human, and then focus on concept neurons that were discovered 20 years ago and have been largely ignored, I think, especially by the community that does animal electrophysiology. I'll be happy to share it here in a community that seems to be focused on specifically human cognition or cognitive features, and then talk a little more about what these concept cells might be good for. So to start with the talk. So the opportunity we have to record these single neurons is when epilepsy patients who don't become seizure-free by taking medication, and if they have what we call a focal epilepsy, then usually there is some part of the brain that starts these seizures. And if you can identify that part and simply resect it, then ideally the patients are seizure-free afterwards and have no neurological or cognitive deficits or impairments. In the vast majority of cases, this whole workup, this clinical workup, can be done non-invasively. But a fraction of less than 10%, I would say, of these patients need to have electrodes implanted in order to decide where the seizure focus is located. These electrodes have been around for 70 years, roughly, and they look a little bit like this over here, and those cylindrical contacts are what records the signal of hundreds of thousands of neurons. Actually, it's not even the neuronal activity, it's the postsynaptic input, the dendritic activity that's being recorded in local field potentials and intracranial EEG, or surface EEG also for that matter. And then some 20 years ago, or 25 years ago by now, a neurosurgeon at UCLA by the name of Itzhak Fried had the idea to use these electrodes that typically have a hollow inner canal where you put in a steel rod to make them more rigid. And he figured if there's a hole in there, a canal in there, why not put a few wires through them such that they stick out at the end. And these wires are so small, they're about as thick as a hair and also almost as flexible. They're so small that they can record the activity of 1, 2, 3 neurons in the surroundings. Because they're flexible, they're considered to pose no additional risk to the patients, which is important because there's also exactly zero benefit for the patients to have them. Then the data I'll be showing is from medial temporal lobe epilepsies, where the electrodes are implanted orthogonally, so they go in from the side about 4 centimeters deep, and then they can be placed, for example, in the hippocampus or in the amygdala and get to record single neuron activity. This is a picture from the OR. So here you see such an electrode. This is the steel rod that's then pulled out, and then here you see me trying to fiddle the bundle of wires in there. So the data I'll be showing today is recorded from these 5 structures. This is our standardized implantation scheme that we use in Bonn, a bitemporal implantation scheme with electrodes in hippocampus, in the amygdala, recently also in the piriform cortex, and then 2 electrodes in the parahippocampal gyrus, one so far anterior that it will hit entorhinal cortex on the medial surface, and the other one so far posterior that it will hit parahippocampal cortex, which is the only region out of the 5 that is indeed neocortex. Here you see one of our epilepsy monitoring units. So the patients are implanted with the electrodes. You'll notice this big head dressing. That is because we have head stages, preamplifiers that need to be as close to the microwires as possible. Because if you were to use a standard cable to get from the head to the amplifier, the whole signal would be completely contaminated from the power outlets in the wall of the room. So that is, unlike the clinical IEEG, the local field potential recordings are extremely sensitive to noise and disturbances. The advantage that we have is that the patients, while they are waiting for seizures under 24/7 EEG video monitoring, have to stay in bed. And that makes them quite willing to participate in experiments, because it simply helps them pass the time. So this is a typical setting. There's a camera here that you can't see that will film everything. If they have a seizure during the experiment, that's bad for us, but good for them. That's what they're there for. If our experiments were to elicit seizures through certain flickering, which first of all doesn't happen in focal epilepsy, and second, if it did, that would be just good for the patient. So this is where we get our data, our recordings, and in a typical patient with these altogether 12 depth electrodes, 6 on each side, after spike sorting, we're able to isolate about 150 plus minus 50 units across these different regions in one patient. And that, of course, is a little bit of a problem, because we're sampling from a brain that has about 80 billion neurons, and if we get to sample 150 of those, then that means we're hopelessly undersampling the system, and the task may seem hopeless. And it's useful at this point to go back into the 1970s, when a discussion was led among monkey electrophysiologists how things in our environments might be represented in the brain. And the two extreme versions of doing that are either using a distributed network code, and as an example here, I just put a bunch of 8 neurons, and if you add the constraint that half of them, 4 of them are always active and 4 of them are out, on and off, then that actually gives you 70 possibilities to align them here. So this small network of 8 neurons can attain 70 different states, which means it could, for example, distinguish between 70 different people that you know. Alternatively, you could simply take 70 neurons, each for every person you want to represent. For example, this neuron over here could represent your grandmother, which means it could fire every time you see your grandmother, every time you talk to her on the phone, every time somebody mentions her name, every time you think about her. And according to textbooks, this is something you should never encounter in a mammalian brain. Because obviously this is a very inefficient and uneconomic way of coding compared to this, especially when you realize that if you increase the size of such a network, the number of states you can differentiate scales exponentially. So there was vast agreement that this is how the brain works, and this is something you should never encounter. And for the rest of the talk, I will try to convince you that there are representations in the medial temporal lobe of the human brain. We don't see them outside of this region, and I would argue we don't see them outside of the human species. So you get to listen to one neuron while the owner of that neuron is being presented with different pictures. Every click is an action potential, and you can tell this neuron has a preference for one of the pictures. So there's some baseline activity, and then every time the picture of Marilyn Monroe comes on the screen, the cell goes crazy. This is something that we observe in virtually every patient that we've implanted in these regions. And the visual version of what you just listened to is this. This is called a peristimulus time histogram. So here's the target stimulus that we're interested in. And suppose it was shown 6 times, then these would be the response rasters. Every blue line here is an action potential, and down here the histogram sums up that activity. So this is 3 seconds worth of data. The first dashed line shows when the stimulus goes on, and this is when the stimulus goes off. So you can see the stimulus comes on, and then 200-300 milliseconds later the cell starts firing in these bursts, which made the sounds that you heard. Now the question is, what was it about the Marilyn Monroe picture that caused the cell to fire? And the possibilities are almost countless. Could be that the cell is interested in women, or in white dresses, or in actresses, or in black and white pictures. It could also be that it really encodes the identity of the person. And so this was the data that we recorded at UCLA, so very close to Hollywood, so it was fitting that we would find a response to Marilyn Monroe. In Bonn, we never saw a Marilyn Monroe response. Instead, we saw a response to Michael Ballack, a soccer player. And again, to address the question, what was it that caused the cell to respond to Michael Ballack, we ran a follow-up experiment where we showed not only his picture, but also his written name and his name spoken by a computer voice, along with pictures and names of a bunch of other people. And it turns out this cell responded only to his face, to his written name, and to his name spoken by a computer voice. This is a replication of findings from Rodrigo Quiroga, the infamous Jennifer Aniston or Halle Berry neuron, a German version of it, I guess. The remarkable thing is that while obviously written words are processed differently from faces, both are visual modalities, whereas a spoken word is a completely different sensory modality. And all of this converges onto this one hippocampal neuron in this case. And we find these types of cells in the hippocampus, in the amygdala, and in the entorhinal cortex. So that distinguishes them, that is one of many, many things that distinguishes them quite strongly and substantially from rodent play cells. Here's another example from the same recording session. Here we had found a response to Harry Potter in a morning session. And then for the follow-up experiment, my graduate student made a mistake, and he clicked accidentally on the picture next to Harry Potter, which was Ron Weasley. Now, if you're familiar with the Harry Potter story, Ron is Harry's best friend, and we know the cell would have responded, did respond to the picture of Harry Potter earlier on. I'm pretty sure it would also have responded to the written and spoken name of Ron Weasley. My guess would be that it also would have responded to picture and name of Hermione Granger. That's the third of 3 friends in the story. And I don't know if it may also have responded to other characters like Lord Voldemort or Professor Dumbledore, or maybe Gandalf from Lord of the Rings, same profession, different story. The reason why I usually show this image is to drive home the point that there is such a thing as semantic tuning. All of us that are familiar with the Harry Potter story will have neurons that are tuned just to one single character, and also neurons that will perhaps be tuned to all of the characters in the story, or maybe to wizards in general. So we have the coexistence of very narrowly and or rather broadly tuned neurons. And at the time, this was just some anecdotal findings. And so the study I want to describe next is one that we did in collaboration with Stan and Yair, where we collected data from a bunch of patients. So this is almost 3,000 neurons that we're talking about. And the idea here was, in our usual screening sessions that we run in the morning, we show a bunch of pictures. And in this particular case, it was pictures of objects that were taken from the so-called Things database designed by Martin Hebert, where you have a bunch of objects, and for each object you have at least 12 different natural images that show the objects. And we had been using this for a while because as soon as we got a response, say to an accordion, when we showed 8 different pictures of the accordion, there was visual invariance in there already by design. But the interesting part here is this: we ran this experiment and at the same time performed online spike detection and spike sorting. So we knew in real time whether neurons responded to any of the pictures. And when we found a response eliciting pictures, we would tap into a semantic space that is also included in the things database, and would look for the nearest neighbors of that object, semantically nearest neighbors, and show those to see if they would also elicit a response, and if this response was weaker or stronger. And if it was stronger, we would take that as the next starting point and iteratively try to find the strongest response eliciting stimulus. And by doing so, we were able to generate something you could call tuning curves, right? Because we knew we had a metric for the semantic similarity relative to the strongest response eliciting stimulus. And this now, so the semantic space, we use the entire space, which has 300 dimensions, and this is just a multidimensional reduction in a two-dimensional space. And what we see is that there are indeed receptive fields for these concept neurons. So here we have an amygdala neuron that is very interested in food, in various food items, and doesn't care so much for musical instruments or anything else. Here we have a hippocampal neuron that is interested in parts of cars, so anything related to the interior of a car elicits a response. And what we can do then is look how the firing rate, the response magnitude changes with the distance to the preferred stimulus. And that way we can see, for example, here you have a slope that is not particularly steep, whereas down here in the hippocampal neuron you have quite a steep slope. And also this tuning, because the rise is close to 1, would be described as rather narrow, whereas this is a broader tuning in general. Down here we have the grand average across all the responsive neurons that we observed. And so this is the typical or average response curve that we observed. And when we looked at the tuning width, we saw no differences across these 4 MTL regions: amygdala, entorhinal cortex, hippocampus, and parahippocampal cortex. And the only striking difference we saw is that indeed the hippocampus shows steeper tuning compared to the other 3 regions. What we could also do with this data is see which models best explained the data that we collected. And there were these 3 different classes: either network-based models, so that could be dendritic or hierarchical, as in this case, or feature-based models, things like, does it have wings, is it a thing, can I carry it? Or continuous vector models, which were derived from, for example, big corpora of work by measuring coincidences of words and things like that. And in addition, the things database has also a human rating, where all of the stimuli were rated in groups of 3 and subjects had to identify the odd one out. So here we have actually a human behavioral rating of semantic distances. And it turns out that across all of these brain regions, and it was fairly consistent within regions also, or across the regions, that the network-based models performed rather poorly. In between there were feature models, and then the continuous vector models were the ones that best explained our data, and but not as good as the actual behavioral data. So that is fairly consistent data in here. We also recently added a new sensory modality to these concept neurons. Because we were recording in the piriform cortex, which is considered to be primary olfactory cortex, we also added olfactory stimuli. So there are commercially available sniffing sticks, and we used these sniffing sticks and just held them under the nose of the patients and then manually locked in the start point. So the timing accuracy is certainly limited, but still we got to record very clear responses. So over here you see an amygdala neuron that responded strongly to the smell of a banana, right? Here you see the 15 or 16 different smells that we used. And interestingly, the same neuron also responded to the image of a banana and to the written word banana. This is an amygdala neuron, and over here we have a piriform cortex neuron that responded to licorice. So here it's the smell of licorice. This is, I don't know if French people know this type of licorice. I know Americans don't, but Germans eat licorice in this way. And then also to the written name licorice. Interestingly, there was also a strong response to one other smell, which is anise, and anise is part of most licorice compositions. So to me it was quite surprising to find a cell like this in an area you would consider primary olfactory cortex. I would never expect to see a concept neuron in V1. So this might point to the fundamental difference of the sensory modality of smell. Anyway, that's the concept neurons that we observe in virtually every patient that we've implanted in these regions. And next I want to show you one remarkable feature, which is the context independence of these concept neurons. And for that we designed an experiment where we use 4 pictures that were pre-screened to elicit concept cell responses, and we show them in different task contexts. And by task context I mean the question that's being asked at the beginning of a trial. So the idea is always to compare 2 stimuli, and it could be by deciding which of the 2 objects is bigger, or which of the images is brighter, which is a purely perceptual question, which is more expensive in case of people who is older, which or who do you like better, and which or who have you last seen in real life, which is a mnemonic question. And we ran a bunch of trials in that experiment, and what we found is, across these experiments and after recording more than 3,000 neurons, is that of course we had a large number of neurons that were modulated by the stimulus. This is not surprising because that's what we screened for, so in a way that's by design. But we found an almost similarly high number of neurons that were modulated by context. Then of course there's an intersection between the 2 neurons that show 2 main effects according to an ANOVA. But what we were mainly interested in was signs for pattern separation, because in rodents, the hippocampus is considered to be the actor for pattern separation, particularly in the subregion of the dentate gyrus. There's supposed to be pattern separation, and the hallmark of pattern separation in this case would be conjunctive coding, to respond to a particular stimulus only in a particular context. And in this statistical evaluation, that would mean we would see a statistical interaction in the absence of any main effects. And that would be this small part over here. So conjunctive coding, in a strict sense, is shown by only 11 neurons out of 3,000 and some. So the remarkable point here is that the human hippocampus, and of course I should add, we have no idea whether we're in CA1, CA3, subiculum, or dentate gyrus, but the point is, across the hippocampus we see no signs whatsoever for pattern separation. That is quite remarkable, and it relates a little bit to another study. So this is an earlier version of our object screening, where we showed 100 different stimuli, 10 categories, 10 stimulus per category, and every picture was shown. In this case it was always the same picture. Every picture was shown 10 times. What we find here across almost 5,000 neurons that we recorded is that about 15% of them responded to one or more of the presented stimuli, half of these to just one, and half to 2 or more. And here are a few examples. So this is an entorhinal cell that responded to different items of clothing. Here you see the different categories and the response strength here. Here we have a cell in hippocampus that responds to a piece of cheese and to nothing else. And here we have an amygdala neuron that responds to all kinds of edible things, man-made food and also the apple. When we we then ran a decoder, so we trained a decoder, we gave it the responses to 9 out of the 10 pictures for each category, and then tested it on the one we left out. And it turns out that the decoder was extremely well at assigning a picture to the correct category. That's what we see up here. We then did a different decoding analysis where we gave the decoder 9 out of the 10 presentations of every picture to train with, and now the task for the decoder was to identify the correct picture, 1 out of 100. So up here the chance probability is 10%, here it's only 1%. And it turns out that still in all of the regions the decoder performed well above chance. But what's quite remarkable is when you look at the error matrix here, where we plot false positives against false negatives, you see that the structure, the errors don't occur randomly, but instead they tend to occur within category, which leads to the phenomenon that what you see here, the shape is almost similar to up here. Right? The mistakes that are being made reflect the category, are typically made within category, and this is the substrate very likely of false memories, a phenomenon well known from psychology. If you give subjects a word list to learn, then probe them with another list, then they will likely create false positives if something that's semantically related is in that second list. So why I'm showing these two studies is to drive home the point that this degree of not only semantic invariance, but also context independent. If I have a concept neuron in a patient, it will fire also when I take the patient to a different building. We have done that, right? The same cell will do the same thing regardless of any of the contexts. And that is something very unusual. That is something never observed in rodents, where you have constant remapping as soon as you change the context, as we just heard in the first talk today. So the way we think of it is we have this enormous degree of semantic invariance and context independence that allows us, for example, to imagine what it would be like to go on vacation with a friend, or if we meet someone, we can instantly retrieve all past experiences with that person. That only works because of this invariance, but this invariance comes at the price of being lousy at pattern separation, right? Because we are not so good at pattern separation is why we make all of these mistakes, which a rodent perhaps wouldn't make. Okay, so the important question in a way is, why would the brain allow itself the luxury of having these very sparse representations when textbooks tell us we should not even be seeing these? And if we realize we find them exclusively in an area that is necessary to encode episodic memories, we know that from HM, the response onset latencies are incredibly late. They're around 400 milliseconds, 300 to 400 milliseconds in entorhinal cortex, hippocampus, and amygdala. The parahippocampal cortex is a lot earlier and differs in many respects from the other regions. We have also seen in different studies that these neurons follow conscious subjective perception. So so this is, for example, a study by Gabriel Kreiman using binocular rivalry. This is one by Rodrigo Quiroga using fast masking. This is one using hybrid pictures, and this is the latest study and also the most comprehensive. Here we used attentional blink. And then we could see whether the cells would also blink or not. And it turns out in hippocampus, entorhinal cortex, and amygdala, they blink. In the parahippocampal cortex, not so much, which in a simplified or simplistic way means at the stage of the parahippocampal cortex, there is probably no no conscious perception yet. And within the 120 milliseconds difference in latency, somehow the conscious perception happens in whichever way and wherever. We don't know, but at least we can say by the time we see these concept cells fire, it already has happened, which of course is a prerequisite if you want to talk about declarative memory, which means you are consciously able to name things. And if you think about that, this is a hypothesis that Rodrigo Quiroga formulated as early as 2012, that basically the function of these cells is to provide the building blocks for memory, because episodic memory basically means you need to encode where was something, when was it, who was there, what happened. That's basically what you need to associate, put together. Associating at the neural level always happens according to Hebb's law: what fires together wires together. And if you want to encode a memory of something that happens, because you can't predict what will happen, and very random things can happen. You can be at a conference like here and walk outside and suddenly run into a friend from elementary school. There is no semantic relationship in that sense, and still you want to be able to encode it. And because of that, you need a system that can independently activate all kinds of representations. And while a network can do very many things very efficiently, it can only do one thing at a time. And in this case, you need to associate a number of different things. And for that, it is very convenient to have these representations, which is why I think it makes sense that we find them, first of all, only in humans, and I'll be happy to debate that, and second, only in the medial temporal lobe. Now, this hypothesis, even though it had been around for 13 years, wasn't tested until very recently, and we simply tried to operationalize it in the form of an associative memory task that we ran with a bunch of patients, and it's an item location association task. So we use pictures, once again, that were pre-screened to elicit concept cell responses. And we showed them on a 3x3 grid on a computer screen. At the time, we did not yet have eye tracking included in our setup, so that is why patients had to press on a touch screen to acknowledge that they saw the location and the item. And there was a series of items that they were supposed to remember. We had a distraction task where they had to count backwards in steps of 3 from a random starting number for about 15 seconds. I realize this is short, but we will consider this long-term memory. And then there's a retrieval phase where in random order they see the image beneath the grid and have to press where they remembered or did not, where the picture was. Now we wanted to compare successful to unsuccessful memory formation. So ideally we would want to have 50-50. Performance, and to achieve that we had an algorithm running in the background and adaptively changed the number of items in one trial to either make it harder or easier for the patients. And the task was simply stopped after 35 minutes, and then we looked at what we had in terms of responses, and here is our 2 single units. The left one responded to a workplace, the patient's workplace. This is from a different patient unit that responded to one of the patient's relatives. And when we now look at, this is during encoding, and when we now look at the subsequently remembered in blue versus the forgotten trials, we can compare those. And what we see is that indeed, for those that are remembered, there was much higher firing of the concept neuron during encoding. And here we see basically the same thing. Much to our surprise, we also saw something in the parahippocampal cortex that we weren't expecting, namely neurons that we ended up calling location neurons, neurons that would respond to a particular field in the 3x3 grid, regardless of which picture was shown. So here you have one that responded whenever a picture was shown in the middle left field. Here's one that was interested in the entire bottom row. And we did the same thing. We compared successful versus unsuccessfully encoded. And here, during the response, we don't really see a difference. And there is something that you wouldn't consider very relevant over here, and I'm pointing it out because it turns out to be indeed relevant. Because when we now look at all of our 3,500 neurons that we recorded, and we first of all look at the concept cells responding to certain items, and as you can tell, that those are less than 10% of the recorded cells were considered concept neurons. But what we see is indeed in the grand average, the activity during encoding allows us to predict above chance level whether something will be remembered or not. And that goes for the amygdala, for the hippocampus, and also for the entorhinal cortex, but not for the parahippocampal cortex. Now for the location neurons, first of all, the number of location neurons were not actually significant in these three regions, so they only did exist in the parahippocampal cortex, and there they indeed predicted successful memory formation, but at a rather late stage, which first of all was very surprising to us, but then we simply realigned the data. Here 0 is onset of the picture, but now we realigned it to when they pressed on the location on the touch screen. So now 0 is the button screen press, and we see it's right after that moment that we see the difference. So it does make some sense. What's perhaps most important is that when we look at all the rest of the cells, more than 90% of the neurons we recorded in these regions didn't care at all about whether something was going to be remembered or not, right? They had no influence at all on whether a memory was formed. So we can show that there is a very, very specific role of these concept neurons for the particular item, that they indeed predict memory formation. And so with that, I'd like to come to an end. We're in the very fortunate position that these concept cells do exist, because if everything was a network code, we'd be hopelessly undersampling it. They show semantic tuning for certain concepts, and it's a graded tuning, but sharper in the hippocampus. They are completely context independent. We also know anecdotally that their selectivities remain constant at least over the course, or there are cells that show a constant selectivity for at least 2 weeks. We don't know what it would look like a year later. We've seen that maybe this independence comes at the price of being bad at pattern separation and thereby forming false memories. We have shown that they actually are semantic building blocks of memory, and specifically in hippocampus, amygdala, and entorhinal cortex, it's item neurons, and in parahippocampal cortex, these location neurons that contribute to the forming of associative/episodic memories. And with that, I'd like to thank the people who did all the work. Marcel Bausch did the context study. Katarina Karkowski is the collaboration with Stan and Yair, did the semantic tuning. Zina Mackay did the association study, and Thomas Reber did the false memory study. And with that, I'd like to thank you for your attention.